We need to solve this for t. You want to get the part that the exponent is on one side by itself. So we'll go ahead and divide both sides by 3. Now that you have the part with the exponent on it on one side by itself, now we can use the definition of a logarithm. We'll write it from the exponential form into the logarithmic form. So we'll go log of our base. Remember, your exponent goes on one side all by itself, and then what was over there goes after your log. Now we want to continue to get your variable by itself, trying to solve it for t. So let's go ahead and get rid of the 4 by multiplying both sides by 1/4. Continuing to solve it for t, so once again, you want to get the part that has your exponent on it on one side by itself. So you want to get a by itself. So you got to get rid of the p. So you're going to have to add p to both sides. And you want to get rid of the m, so you have to divide both sides by m. Once you have your part with the exponent, this part right here, on one side by itself, then you want to use definition of a logarithm. So you go log of your base. Remember, your exponent goes on one side by itself. What was on the other side goes after your log. Then you want to finish getting n, or t by itself, so you want to get rid of the n. Multiply both sides by n, and then you get t by itself. Here we have a single log on the left, a single log on the right. Both of the same base. Since we have one log on the left, one log on the right, and they have the same base, then we can drop the logs. You could not drop the logs if you had multiple logs on one side. So you drop the logs from both sides, because there's one log on each side, the same base. Then you just solve your equation. So you get your x's on one side by adding an x to both sides. Get rid of your 4 by subtracting a 4 from each side. Do a little bit of division. And then you want to check your answer. If we go ahead and take this right here and plug it in here for x and here for x, does it cause what's after your log to be negative? Because remember, nothing after your log can be negative. Negative 1.5 plus 4, well, that's going to be positive. 1 minus negative 1.5 would be a 1 plus 1.5, which would be positive, so yes, it does work. Same on this one here. Single log on each side, so we drop the logs. Solve what's afterwards. Subtract an x from both sides. We go ahead and we divide by our 5, we get negative 1. Then we want to check to see if plugging in our negative 1 here for our x causes what's after your log to be positive. Well, when we plug it in here on the left, a negative 1 minus 5 is negative. Since it causes us to get a negative after a log, our answer is the empty set. We want to go ahead and solve these for x. Right now our x has a log by it. There's no base written, so it's assumed to be base 10. Because this is a common log, which is log base 10. Once you think of it as a log base 10, you want to get rid of your log. So we're going to put it in the other form, the exponential form. So we're going to take our 10, swing it over, and it hits the negative 4 up as the exponent. And when you do that swinging, then the log drops. We now need to get rid of the squaring. To undo your squaring, we'll take the square root. Square root of the x squared is x. Square root of the other side, you should remember, is plus or minus. Remember, your square root is a fractional exponent of 1/2. You now have an exponent raised to an exponent. Remember, you want to multiply those together. If you want to write this without a negative exponent, remember your negative exponent tells you to go 1 over, and then it would be a 10 squared, or 10 to a positive 2, which is a 100. And in this case, the plus works and the minus works, because even if we put the negative 1 over 100 in here and square it, is what's after your log going to be positive after you do the squaring? Yes. Over here on the right, we're dealing with e, which is your natural number e. We also have a natural logarithm, which remember is your log base e. We're going to just rewrite our exponents here, because we want to look at this in terms of your e and your natural log kind of being grouped together. Here you were just at an x times your natural log of 2. Here we just have your x times your natural log of 2. All we did was switch the order. Now, your natural log of 2, remember, is really just log base e of 2. One of the properties of logarithms says that when this base here is equal to the base in your exponent of your log, they undo each other, leaving you just with what was after the log. So it's just 2. Everything in the parentheses reduces down to 2. Still going to be raised to the x power. Still going to be equal to the 1/4. Now we need to go ahead and get x by itself. Right now it's in the exponent. So we're going to use a logarithm, or not. You could use logs. Another way to do it, though, is by using the idea of this is 2 to a power. Can we somehow rewrite 1/4 as 2 to a power? Be 1 over a 2 squared, which you should remember would really be a 2 to the negative 2. And so that's what we have written here. Two to a power on the left equals 2 to a power on the right, so therefore your exponents have to be equal. Here we want to go ahead and graph our log y equals log of x. So we'll just make a t-chart. If you want, since this is log base 10, you could use your calculator. You could also think about what this means to be able to come up with some of these. But whether you use your calculator, go to log of 0.01 and you get -1. Log of 0.1, you get -2. Log of 1 is 0. Log of 2 is about 0.3. I'm only going to go to 1 decimal point since we're graphing it. It's hard to get it any more accurate than 1 decimal point on a graph. And then just continue to go ahead and graph these. Plot your points that we just got. When you plot your points of those, we end up with this. Now, keep in mind that when you plot your points and connect these, there's really an arrow going here, and then this really goes down forever right here. There's a vertical asymptote that's occurring. Now, you should realize that if we were looking at y equals log of x plus 2, that all that's going to do is just shift your graph up 2 units. So we're going to take the graph we just had on the previous page and redo it, just moving it up 2 units, and we get this. On the far right over here, remember when you're dealing with adding or subtracting, affecting the x before you apply your function, it affects it horizontally. In this case, it's going to move it 2 units left. So we'll take our normal log graph, just move everything 5 units to the left. And so then we get that graph. Once again, there'd be arrows on each side here.